there are many, many ways that we can model non-ideal gases. We're just going to look at one particular example. So what if it's not obeying the kinetic molecular theory? And like I said, the two premises most likely to cause deviation are the factor that gases do have attractions, many of them. Yeah, maybe not hydrogen, maybe it doesn't have a whole lot, but water, wow, water has hydrogen bonding, very strong attraction. You know, hydrogen's only London dispersion, and water has hydrogen bonding. So given the same pressures, you would certainly expect to see greater deviations. And so this is your observed pressure, and this would be a correction to account for the fact that there are intermolecular forces. So this would be your PV is equal to nRT. So there's simply correction factors to the ideal gas law. And this corrects for molar volume or molecular volume. For very, very large gases and or gases that are really squished tightly together. Okay, and both of these are going to happen at high pressures. You're going to squish gases together, so they'll sense that intermolecular force, right? Whoops. They'll sense that intermolecular force, right? And they'll start to take up the volume of the gas will take up a significant amount. In other words, the volume of the gas will no longer be much, much, much less than the volume of the container, and so we can't ignore it anymore. This also happens at low, very low temperatures, so it's non-ideal. I just said it the opposite of what we had above, right? Okay, non-ideal. So this shows a ideal gas graph, right? You should know pressure versus volume, right? And then this shows a real gas, and you see those deviations up here, especially at high pressures. Once we got to low pressures, those curves start to become closer and closer together. So the greatest you increase the deviation from ideal at high pressures. Okay, and this is another way to do this. If you take PV over RT, right, an ideal gas would be a straight line here versus pressure. And the greater the intermolecular forces, the more it deviates, right? So ammonia deviates because of that hydrogen bonding. It deviates continuously. Okay, CH4, London dispersion forces. So as you get to higher and higher pressures, you start to see more and more deviations. So those constants are tabulated. You won't be doing calculations with this. This is more of a qualitative understanding of one way to talk about ideal gases. One more left, kiddos. Until then, this is signing off.